coming to the methods to monitor the progress of reaction. Okay, these are all, in fact, some examples of the first order reactions that I'm going to take, right? And see, we are going to monitor the progress of the reaction, taking one of the property into consideration, like for example, pressure or volume, okay, or sometimes the optical rotation. But remember one thing here, you are not given any information about the reactant, which is normally given. In general, till now, we have seen problems, we have seen theory wherein we have taken the reactant into consideration, the concentration of the reactant into consideration especially. But in these cases, will be given something else. I mean, we are given something about the reaction or about the progress of the reaction other than the concentration of the reactant, mostly about the product. Okay, let me tell you that. Now considering the pressure, okay, in this particular case, let me take my first example, that is decomposition of N2O5. Now within this, the first condition that we are going to impose is when P naught and PT are given. Let me tell you what this P naught and PT are. Consider this reaction, which is a first order one. For this reaction, first of all, look at the ratio in which they are reacting and forming. See, for this reaction, the pressure at time t is equal to 0. This is what I call P naught, or you can say P0. Okay. Initially, we will not be having any of these products. Now, pressure what has reacted, or let me say decomposed. Reacted is anyway taken as X always. Now, following the ratio, X gives rise to 2X here, and in this case it is X by 2. Okay, look at this. 1 is giving rise to 2.5. Similarly, X gives rise to 2X and X by 2. Now this is pressure decomposed. And finally, pressure at time t. Of course, time t is equal to t. Okay, so that can be given as P naught minus X, isn't it? See, overall, course, this can be given as PT. Now, PT can be given as, pressure of the total mixture at a time t can be given as P naught minus x plus 2x plus x by 2, right? Now, this can be written as P naught plus x by 2, nothing but P naught plus 3x by 2, right? So this is PT. Now, anyway, they have clearly mentioned, they have already given the values of P naught and PT. Now, these two are given. X, of course, can be calculated, isn't it? Only one variable, one thing to be calculated. Now, after calculating this, we can simply substitute the things in the expression for first order rate constant, that is 2.303 by t into log, of course, a by a minus x, but let this a be taken as initial, right? Let this be P naught. Now, when this also is P naught. So, A is a P naught. Therefore, it becomes log of P naught by P naught minus x. Let me write the final expression once again. Therefore, K1 is equal to 2.303 by T log P naught by P naught minus x. Now, look at the whole thing. You are not given the concentrations of the reactant, initial, reacted, and left out. Instead, they have given the pressures. That too, pressure at time 0, pressure at time t. These two are given, from which we have calculated x, the amount that has reacted or the pressure that has decreased or decomposed. Then finally, we have calculated K1. Okay, so this is how we'll be monitoring the progress of the reaction, taking the pressure into consideration. Now, let us go for the second variety. Now, within this, let us go for something else. When PT and P infinite are given, okay, look at this. As usual, pressure at a time t is equal to 0. Okay, P0, then pressure reacted or decomposed is x. Now, when x reacts, we get a 2x and x by 2. Then pressure at a time t is equal to t. This will be P naught minus x. Okay. Then I can actually tell you this in some other way, as pressure decomposed in say time t, right? Now, then pressure after time t or at a time t? It is because here we are going to get something else. Pressure decomposed in a infinite time. I mean, after a very long time, when you are considering something after a very long time, whatever is being taken will surely react, isn't it? Now when P naught or P0 reacts, it will be obviously 2P naught, then P naught by 2. So the pressure at time t is equal to infinite. You have taken P naught or P0 and then the total thing is already reacted or decomposed. You will be left with nothing, zero. So, you know, this is anyway P, say this is PT, right? And this is your P infinite. Now, let us consider the whole thing here. P infinite can be written as, come on, 2P naught plus a P naught by 2. This comes out to be 5 P naught by 2, right? 5 P naught by 2. Now, anyway, P infinite is given, right? So, this can be calculated. See, you are not given this P naught. This, of course, can be calculated. Okay. Now, let us go for PT, which is also given. Look at PT. Nothing but P naught minus X plus 2X plus X by 2. So, this can be given as P naught plus 3x by 2, as we have seen in the previous case also, right? Now, even here also, PT is given. We have calculated P naught in the previous step. Let me say already calculated. Now, this X can, of course, be calculated. That's it. You got your X. You can calculate K1. So, K1 is equal to 2.303 by T log A by A minus X, isn't it? Now that A again is of course P naught, but the way P naught is calculated is interesting here, isn't it? You are not given P naught, but you have calculated it making use of PT and P infinite. Come on, K1 is finally 2.303 by T log P naught by P naught minus X. So this is how we can actually monitor the progress of the reaction, taking the pressure into consideration. So let us go for the second thing that we generally consider, volume measurement. Okay. Now in this, there are of course different varieties. Coming to the first one. Now here, we are given the volume of a product. Taking the volume of a product into consideration, we'll be monitoring the progress of the reaction. This is going to be very interesting. same first order reaction carried out in a solvent, CCl4. Now, as I said, we are not given anything about N2O5. No, we are not given any information about this. But we are given information about the volume of oxygen at a different times. Okay, so by taking the volume of oxygen into consideration, we'll be monitoring the progress of the reaction. Now, let us take Vt as the volume of oxygen liberated in a time t. But what does that indicate indirectly? Now, see, volume of oxygen liberated in a time t, can it be given as the volume of N2O5 that has reacted or decomposed? Isn't it? Because no, only when this N2O5 decomposes, you will get oxygen. So whatever N2O5 decomposes in time t, that is going to give you the volume of oxygen in time t. So let me just give this as, now this can be simply written as liberated volume of oxygen liberated in time t can be given as a directly proportional to volume of N2O5 that is decomposed in time t, right? That is very interesting. Now, how about V infinite? Now, this is in fact the volume of oxygen liberated in infinite time. What does that indicate? Now, as I said, if you consider this final information, whatever volume of oxygen that we'll be getting after infinite time is nothing but the volume of N2O5 what we have actually started with. Because this whole thing will react and will liberate maximum volume of oxygen, and as far as this is concerned, you will be left with nothing, zero, because this is after infinite time. Okay, so after infinite time, whatever N2O5 we have started with completely decomposes and the whole thing is liberated as the volume of oxygen. Now we'll be left with nothing. That means the total amount what we have started with has actually reacted. So let me write this volume of oxygen liberated in infinite time as directly proportional to the volume of N2O5 taken initially. Okay, now decomposed in time t is your x, taken initially is your a. This is very interesting. Now, as usual, let us substitute this in the expression. K1 is equal to 2.303 by t log. Of course, it is a by a minus x. But now this a and x have got some other terms. Come on. K1 is equal to 2.303 by T log. What is A here? Nothing but V infinite by again A is V infinite minus X is Vt. Is that okay? So this is how we can monitor the progress of the reaction when the volume of one of the products is given. Okay. Now coming to the second one. See, by titration method also we can monitor the progress of the reaction. Let me just go with one very interesting example. Decomposition of hydrogen peroxide. You know, hydrogen peroxide decomposes to give water and oxygen. Now remember, progress of this reaction is monitored not by the information about hydrogen peroxide, not even by the information about the volume of oxygen, but by something else. Very interesting. Progress of this reaction is monitored by titrating the hydrogen peroxide against potassium permanganate. So this makes it very interesting. Come on. Now remember, whatever hydrogen peroxide that you have will be, of course, reacting with KMnO4 during the titration. Okay, the titer value is going to give us the amount reacted, the amount that we have started with of hydrogen peroxide. Now, suppose if I say volume of KMnO4 used up at a time t is equal to 0. That means when we are just about to start the reaction, can this be given as? Because whatever KMnO4 that we are using now at a time t is equal to 0, that will give us information about the volume of hydrogen peroxide that we have started with. Because I said that the KMnO4 is no doubt going to react with hydrogen peroxide. So this can be given as directly proportional to the volume of hydrogen peroxide taken initially or at the beginning of the reaction. This is nothing but our A. Simple. Similarly, the volume of KMnO4, you go for a titration again after some time, used up at a time t is equal to t, then that will give you the volume of hydrogen peroxide present at a time t, isn't it? present at a time t, or you can say left at a time t, whatever is present at that particular time. So nothing but a minus x, because whatever is left at that particular time is going to actually get titrated with K-4. That's it. The K-4 will react with whatever amount of hydrogen peroxide is present at that time. At time t is equal to 0 will give us the initial volume of hydrogen peroxide. A by A minus x. Now this is V0 and this is of course Vt. So this can be given as K1 is equal to 2.303 by T log A is a V0, A minus X is Vt. Right? This is very interesting. By titrating against KMnO4, we have monitored the progress of the reaction. And see here, no information about hydrogen peroxide, indirectly given in the form of volume of KMnO4, but still we could manage to